Welcome. You're listening to an exclusive deep dive, an authoritative briefing tailored solely for above-the-norm news subscribers. Today, we are taking the time to look at a genuinely paradigm-shifting piece of scientific research, an investigation that really reinterprets nearly a century of physics, published in the journal Classical and Quantum Gravity.
Indeed. What we're doing today is a serious and I think a very necessary reassessment of one of the most enigmatic concepts linking general relativity and quantum mechanics, and that is, of course, the Einstein-Rosen bridge.
Right, the ERB. For decades, it's been synonymous with this almost fantastical idea of a wormhole, a geometric shortcut through space-time.
A shortcut that, as we'll see, completely missed the original point.
Our sources for this deep dive are, as always, rigorous. We are analyzing the paper by Gustanyaga, Sravan Kumar, and Marteau. And this isn't a work that just tweaks existing theories. It fundamentally rewrites decades of assumptions about how gravity and quantum mechanics interact at their deepest, most fundamental levels. This is the deepest, most critical analysis of that work you'll find anywhere, custom-built for our above-the-norm news audience.
And the revelation at the heart of this, the core finding of the research, is, well, it's stunning.
Yeah.
The classic understanding of the Einstein-Rosen bridge as a geometric wormhole is fundamentally flawed.
Flawed because that interpretation, the one that blossomed long after the original paper, entirely missed the essential point.
It did.
Because the original 1935 vision by Einstein and Rosen was never about classical traversable shortcuts through space. It was a profound conjecture, and it was rooted in quantum structure. It was tackling the foundational incompatibility between gravity and quantum theory right at the horizon of a gravitational field.
And the core thesis we're uncovering today is that the ERB is actually a hidden quantum mathematical bridge.
A mathematical one.
Yes. And critically, this bridge doesn't connect two distant points in space.
So not a wormhole.
Not in that sense, no. What it does is link two orthogonal sectors defined by, get this, opposite arrows of time.
Which establishes a concealed temporal structure.
Right there, within the very fabric of space-time.
In this hidden structure, it's formalized within a theoretical framework called direct-sum quantum theory. We'll be referring to it as DQFT.
And this is far more than just abstract mathematics.
Far more. DQFT promises to deliver a unitary, and for our listeners, that means an information-preserving description of quantum field theory in curved spacetime. And in doing so, it directly addresses the deepest, most unresolved mysteries in all of physics.
Everything from the black hole information loss paradox
to startling, well-known anomalies that we can actually see in the cosmic microwave background, the CMB.
Our mission today is to uncover the layers of this structure for you. We'll begin by reviewing the historical quantum crisis that Einstein and Rosen first identified, which showed why our standard definition of time it breaks down near gravity.
Then we will explore the precise logic of DQFT and how it reinterprets quantum mechanics using these dual temporal sectors.
And finally, we'll examine the groundbreaking observational proof brought to light exclusively by above-the-norm news that demonstrates this quantum bridge is actively operating right now across cosmological scales.
Okay, let's unpack this monumental shift. We need to start with the historical crisis that necessitated such a radical solution in the first place. We have to go from standard physics into the geometry of horizons.
Exactly.
The long-standing problem of unifying gravity with quantum mechanics has always circled back to the nature of time. When physicists first created quantum field theory, they were working in a very simple environment, flat Minkowski spacetime, far from any serious gravitational influence.
And that QFT, it relied on three core pillars. You had locality, unitarity, and renormalizability. But crucially, underneath all of that was an assumption. The assumption was that time is just a simple, external fixed parameter flowing inexorably in one single direction.
And that assumption works beautifully for particle physics in a lab.
Perfectly. But the moment gravity, and specifically the intense gravitational fields that create horizons, the moment that enters the picture, that fixed definition of time immediately causes the entire structure to break down.
It's remarkable to think that Einstein and Rosen, nearly a century ago in 1935, were the very first to bump up against this central incompatibility.
They were trying to do something that seemed simple. They were attempting to describe the quantum properties of an electron near a black hole horizon.
Before we even really had a solid concept of a black hole.
Exactly. And they just ran into a wall. The math didn't work.
And their deduction from that was, It was just so far ahead of its time.
It was there they couldn't make the standard single-time arrow physics work. So they conjectured that our physical world, the one we observe, must actually be described by, and this is their phrase, mathematical bridges connecting two sheets of space-time.
And that these bridges inherently involve two eras of time.
Yes. They realized, right at the conceptual starting line, that the standard quantum treatment of time was simply insufficient in a gravitational context. It was a dead end.
And this realization, it really forms the foundation for the unitarity loss paradox, which has plagued physics since Hawking's work in the 70s.
It has.
For a local observer, say someone situated just outside a black hole horizon, that observer is fundamentally causally cut off from the entangled region inside that barrier.
And if you're causally cut off from an entangled partner, you lose information. It's as simple as that. The central dogma of quantum field theory in curved spacetime, or QFTCS, is that for that local external observer, a pure state, which is a complete description of reality.
A complete quantum state.
Yes. It evolves inevitably into a mixed state.
Yes.
Unitarity, the essential rule that information must be preserved, is lost locally.
Because you can't access the other side of the entanglement. You can't see what's in that hidden region behind the horizon.
So the ultimate challenge, the one that Einstein and Rosen set nearly 100 years ago, and which physicists are still grappling with today, is this. Can an observer's description of their causally accessible world, can it still remain mathematically complete, a pure state, even when they are separated from the rest of the entangled system by a horizon?
That is the defining question, isn't it?
It is. And it's not just black holes. This is what's so fascinating. Schrödinger, working totally independently in 1956.
Right.
He was looking at the expanding de Sitter universe, which also contains a horizon, and he reached a strikingly similar conclusion.
He called for thin, rigid rods to manage the antipodal identification of space-time points. A different language, but the same idea.
The exact same idea. And then more recently, 2016, Gerard Hoof proposed physically identifying parallel regions outside the Schwarzschild black hole.
So you have all these independent lines of inquiry ER, Schrödinger, Tudor, pointing toward the existence of some kind of mathematical structure that connects seemingly disparate regions separated by a gravitational boundary.
A bridge.
A bridge. And what's truly fascinating, and what the paper we're discussing today highlights as the singularly unifying concept across all these scenarios, is the unexpected mathematical core tying all horizon physics together. And that is the inverted harmonic oscillator, or IHO.
The IHO. This is the structural element that universally appears when you analyze quantum dynamics near any gravitational horizon. Whether it's a black hole, the de Sitter space of the early universe, or even the Rindler spacetime you get from extreme acceleration.
This isn't just a loose analogy.
No, it is a profound, non-trivial mathematical link. The appearance of the IHO replaces the standard, stable physics of the regular harmonic oscillator, and it tells you, mathematically, that you have crossed into a regime where standard QFT fails.
So to really appreciate this, we probably need to understand the fundamental difference between the IHO and the simple oscillator we all learn about in high school physics.
Right. The standard oscillator describes stable, predictable motion. Think of a spring bouncing back and forth or a pendulum swinging.
Because it's Hamiltonian, its energy function is bounded from below. It represents stable, predictable, oscillatory motion.
Exactly. The inverted harmonic oscillator, on the other hand, has a potential that is unbounded from below. It's like a negative parabola, an upside-down bowl.
Which signifies exponential instability, an immediate runaway effect.
And this is exactly what happens at a horizon. Gravitational collapse or cosmic expansion creates an exponentially unstable environment.
So its classical phase space trajectory isn't a stable, closed loop.
No, it's an open, diverging hyperbola. And that hyperbolic structure, the geometry of instability itself, is the key that unlocks the entire ER bridge concept.
So if the IHO is unstable, how does it connect back to the dual time arrows that Einstein and Rosen predicted?
Well, the IHO's phase space, if you map it out, it exhibits 4 distinct regions. These regions are separated by what are called phase space horizons or separatrices. And critically, the classical solutions in these 4 regions are doubly degenerate.
Doubly degenerate, meaning what?
Meaning, for every point, there are 2 possible states. And these 2 states inherently exhibit opposite arrows of time flowing out from the center of that instability.
So the geometry of the IHO's phase space diagram, it's a perfect mirror of the conformal diagrams we use to describe black holes and Sitter space.
It is not a coincidence. It is the universal quantum fingerprint of a horizon.
And this brings us to the pioneering mathematical work of Berry and Keating BK back in 1999. They were looking at the quantum mechanical description of this exact object, the IHO.
Yes. And they found an absolutely non-trivial, jaw-dropping connection between the IHO's quantum structure and one of the deepest problems in all of mathematics, the zeros of the Riemann zeta function.
They showed that in order to correctly quantize the IHO, you had to impose a very specific, rather odd boundary condition.
That's right. The BK proposal demanded identifying those doubly degenerate regions in phase space, those regions with opposite time arrows, and stitching them together.
They called it a mathematical bridge.
They did. But the connection lacked any clear physical or geometric interpretation at the time. It was a mathematical necessity, a trick to make the numbers work, but not a physical theory.
So the significance becomes clear. The exponential instability of the IHO replaces standard stable physics precisely when gravitational horizons are involved.
Yes, the IHO is the mathematical signature of a quantum regime where time cannot be treated as a single, simple parameter.
And where separate regions of spacetime must be mathematically linked.
So the historical quantum crisis identified by ER, the paradox of unitarity loss, and the mathematical conundrum of the IHO quantization. They all converge on the same necessity. We need a new foundational structure for quantum theory itself that can handle these dual temporal sectors that are demanded by gravitational geometry.
We need the physical interpretation for those BK boundary conditions.
And that physical interpretation is precisely the focus of our next section. It takes us into direct sum quantum theory.
So direct sum quantum theory, or DQFT, this is what the paper presents as the long-awaited solution.
It is. It provides the precise geometric and physical interpretation that was missing from those Berry-Keating IHO's boundary conditions. It formally realizes the original Einstein-Rosen mathematical bridge conjecture.
Let's define the direct sum concept itself, because this challenges one of the most foundational rules of quantum mechanics that we're used to, which is superposition.
Right. Standard quantum mechanics, or QFT, requires you to choose an arrow of time to define what positive energy even means. If you define time type flowing forward, you use one sign in the Schrödinger equation. And that single choice defines your entire Hilbert space, your complete set of all possible states.
It's a fundamental choice you have to make at the beginning.
It is. DQFT removes this necessity by acknowledging that this choice only defines one sector of a much larger unitary reality.
So instead of a single state vector, let's call it psi wrangle, existing everywhere, DQFT describes the quantum state of the total system as a direct sum of two orthogonal components. And these components exist in parity conjugate regions of physical space.
The full state is written as psi wrangle left ps right wrangle right.
And that plus sign in the circle, the direct sum operation, that's the key.
It's the entire key. Think of the direct sum operation, the Pluster-Rohnlow, not as mixing like in superposition, but as combining two entirely independent orthogonal realities into one total system.
So it's like having two separate hard drives running the same program.
That's a great analogy. They don't interact locally. They're just considered part of the same physical computer.
Which means the overall Hilbert space is decomposed into what the paper calls geometric superselection sectors, or SSS.
And these sectors are related by discrete space-time transformations, specifically parity, which is mathcal, and time reversal, mathcalic, or the combination, mathcal-p.
And the geometric meaning is built right into the evolution of these states.
It is. The left psi plus right wrangle component evolves with time dpa from -infinity to +infinity. That's our standard forward-flowing physics.
Right.
But the left psi right wrangle component evolves with time in the opposite direction, from +infinity back down to -infinity.
And that is the concealed temporal sector.
That's the hidden part of the reality.
Okay, let me stop you there. If the psi minus component is evolving backward in time, how do we know we're not just describing some non-physical, mathematical phantom? How do you ground that in our everyday physics where time clearly only goes one way?
That is the critical question, and DQFT provides a really elegant answer. Crucially, both components, left psi plus right wrangle and left psi, represent positive energy states.
Ah, okay.
This is the breakthrough that stabilizes the whole theory. Historically, if you time reversed a quantum state, you often ended up with negative energy solutions which are non-physical. They're unstable.
They break everything.
They break everything. By placing the two opposing time flows into these parity conjugate regions of physical space, DQFT ensures that both sectors remain positive energy. You get a consistent physical description without needing two non-interacting parallel universes. They are orthogonal, but they are complementary parts of one system.
So the two sectors are related by symmetry, but they are completely orthogonal in the Hilbert space. This is the geometric superselection rule.
Yes, and it means that local physical operators, anything we can measure or interact with on our side of the horizon, cannot mix these two sectors. You can't reach across.
That orthogonality is the realization of the ER bridge. It's a quantum temporal link, not a spatial one.
Precisely. And this new structure, it imposes a fundamental new causality condition on the total field operator, which is fraft right.
And what's that condition?
The operators that define the two sectors must commute between mathematical points for it. So left x, which rights.
Which is fundamentally different from standard QFT.
Completely different. Standard QFT just requires that operators commute at space-like distances. This new condition ensures the physical independence and the orthogonality of the two temporal sectors, locking them into their own geometric boundaries.
Okay, let's circle back now and connect this new DQFT structure to the IHO puzzle from the first section, that Berry-Keating quantization that lacked any physical meaning.
Right.
How does DQFT provide the geometric meaning for the non-trivial zeros of the Riemann zeta function?
Remember that the IHO's hyperbolic phase space had those four sectors, and two of them were doubly degenerate and had opposite arrows of time.
And the BK boundary conditions required mathematically linking them, but gave no physical reason why you should.
And DQFT provides the reason. So the IHO phase space must be treated as geometric superselection sectors defined by mathematical symmetry. So those doubly degenerate regions are therefore split into four commuting sectors that evolve under this new direct sum Schrödinger equation.
So the mathematical necessity that Berry and Keating found, that certain points have to be identified to quantize the system, is physically realized by the DQFT mandate that these points belong to the same total system but exist in orthogonal temporal sectors.
Exactly. The math that generates one of the deepest mysteries in number theory, the zeros of the Riemann zeta function, is, according to this research, a direct consequence of the dual temporal structure required by quantum mechanics near horizon.
That is a stunning, stunning level of unification.
It is. The transition from standard QM to DQFT, guided by the mathematics of the IHO near horizons, is the fundamental quantum bridge Einstein and Rosen envisioned all those years ago.
It provides the blueprint for quantizing gravity by redefining the role of time at boundaries.
And it's a perfect example of the hidden physics that we are dedicated to investigating for our Above the Norm News subscribers.
Okay, so now we have to shift our focus to the practical implications of DQFT on gravitational horizons. We have to take this from abstract theory to the ultimate proving ground, the Schwarzschild black hole, the SBH. This is where the black hole information paradox is either solved or it's reinforced.
Right, and when we look at the quantum SBH using what are called the Kruskal-Sekres coordinates, which are essential because they smoothly map both the interior and exterior of the black hole at the same time, the conformal diagram is not just conceptually similar to the IHO phase space. The paper demonstrates they are mathematically analogous. It's a one-to-one mapping.
And that analogy is crucial, isn't it? The four distinct regions of the SBH, the two exterior regions, I and 2, and the two interior regions, 3rd and 4, they map precisely onto the four sectors of the IHO phase space.
And under DQFT, these four regions in the SBH diagram become geometric superselection sectors, related by the mathematical T transformation, just like the IHO sectors were.
So region I, our exterior universe, that's the PSA plus component.
And region 3, the interior, the singularity-bound region, is its mathematical T conjugate. It's the TSI component, evolving with the opposite arrow of time.
This entire structure, though, it relies on a really fundamental insight. The paper shows that the quantum operators describing the field near the horizon, they do not commute. Can you explain, in simple terms, why the operators near the horizon must stop commuting for this theory to work?
Certainly. In standard quantum mechanics, operators that represent different independent measurements usually commute. It means measuring one doesn't affect the other. If they don't commute, it means they are fundamentally linked. They're non-independent.
And this non-zero commutator, left, right, at right, nowhere, which was originally derived by S. Hooft based on gravitational backreaction effects.
Right. It indicates that the quantum state inside the horizon is not independent of the quantum state outside the horizon. They're linked.
And in fact, assuming that the operators do commute, that the incoming state is independent of the outgoing state, that's exactly what led to the information paradox in the first place.
It is. You are assuming independence where the gravitational geometry itself requires dependence.
The non-commutativity is the essential physics of the quantum bridge.
It means the system must be treated as a single, coherent unit, even if we are causally separated from part of it. And now, this brings us to restoring unitarity, the biggest challenge raised by Hawking's original work.
The traditional non-unitary fix, the one that's often summarized by the thermofield double state, uses a superposition of interior and exterior states to maintain a pure state overall.
And that approach, it's mathematically convenient, but it's physically problematic.
Why?
Because a coherent superposition, like the thermofield double, implies that the interior and exterior states exist in the same Hilbert space. But general relativity tells us that the temporal parameter, the very definition of time, is inherently different inside and outside the horizon.
So you can't coherently superimpose states from two Hilbert spaces that are defined by different temporal metrics.
You can't. It's like trying to add apples and the concept of democracy.
Mm.
They're fundamentally incompatible domains.
And this is where the direct sum structure saves the day.
Precisely. DQFT replaces this flawed superposition with the direct sum. It treats the exterior and interior as orthogonal yet complementary sectors of a single physical quantum system.
So if superposition is like mixing two paints together to get a new color,
Then direct sum is like looking at two completely different canvases simultaneously. They are distinct, they don't influence each other locally, but they form a complete unitary piece of art together.
and the consequence of this for the information paradox is monumental.
It is. DQFT demonstrates that any entangled state across the horizon splits into a direct sum of pure state components. The formula is the von Neumann entropy of each of those components is 0.
Which means unitarity is locally preserved for any observer.
Exactly. The information is not lost. It is meticulously encoded in the mathematical conjugate superselection sectors. The observer outside sees a mixed state because they are only observing their half, the PS plus dollar part, but the total system, which includes the necessary temporal conjugate, remains perfectly pure.
This brings us to a totally redefined interpretation of the powerful ER-EPR conjecture, the idea that entanglement equals space-time connectivity.
Right.
The original interpretation of ER-EPR involved these non-traversable geometric wormholes connecting two distinct black holes, usually in an anti-de Sitter context.
That traditional view required a connection between external boundaries, between two separate spacetimes, but DQFT provides a horizon-local realization. The connectivity is not geometric travel, it is the mathematical direct sum operation itself.
So the Einstein-Rosen bridge is not a geometric wormhole.
It is a quantum temporal link between mathematical conjugate regions within a single black hole spacetime.
The horizon, then, acts like a PT mirror. The external and internal observers share complementary information in the form of pure states, which upholds the principle of observer complementarity.
The crisis was never the loss of information. It was the physics framework's failure to account for the necessary dual temporal sectors that are required by the geometry of gravitational instability.
So this solution completely bypasses the need for speculative Planck-scale physics or exotic wormholes or entanglement islands to save unitarity.
It shows the resolution was hidden in the foundational treatment of time and symmetry in QFTCS all along. We just needed the mathematics of the inverted harmonic oscillator and the geometry of the direct sum to put all the pieces together.
A theory that solves the black hole information paradox without resorting to physics beyond the standard model and without requiring infinite energy. It almost seems too good to be true. It must be testable.
It is.
And our next section delves into the exclusive proof revealed by Above the Norm News, the observable signature of this quantum bridge in the very structure of our cosmos.
The concepts we've discussed so far, the inverted harmonic oscillator instability and the direct sum quantum bridge, are incredibly powerful theoretical structures. But physics remains an empirical science. If this hidden quantum structure is real, if these temporal sectors are truly orthogonal components of our reality, then they must leave a footprint.
A signature.
A signature. And the most suitable laboratory for testing horizon dynamics is the early universe, specifically the period of cosmic inflation.
Inflationary cosmology describes an extraordinarily rapid, exponential expansion of space, which is governed by what we call quasi-de Sitter, or QDS, spacetime.
And critically, the geometry of QDS spacetime exhibits the exact same IHO physics we identified earlier. The instability of the early universe is mathematically identical to the dynamics near a black hole horizon.
So the logic is inescapable. If DQFT is correct for black holes, it must also be correct for inflation.
It has to be. And when we apply DQFT to that inflationary epoch, the quantum fluctuations that later seed all structure in the universe.
The galaxies, the clusters,
Yeah.
everything.
Everything. Specifically, the Mukhonov's-Sasaki variable, which combines both metric and the inflatant field fluctuations, these are treated as a direct sum of components spanning the mathcal T conjugate regions.
And since the quasi-de Sitter background is a dynamic, evolving environment, it slightly breaks the perfect mathcal T-symmetry.
And that asymmetry is not a flaw in the theory. It's the mechanism that makes the theory measurable. It's what leaves the signal.
And this dynamic breaking means the resulting dqft vacuum is mathcal T ASA P SCAZ plus wrangle QD SCSCO plus wrangle QDSEC is what happens next.
This asymmetry leads to a profound consequence that manifests on cosmological scales. It means a single quantum fluctuation when viewed across antipodal points.
Points separated by the diameter of the observable universe.
Yes, it evolves asymmetrically. The fields on one side of this mathcal T mirror are slightly different from the fields on the other, and this results in unequal two-point correlations when these cosmological modes exit the horizon during inflation.
And this asymmetry isn't just some theoretical noise. It is imprinted directly onto the cosmic microwave background, the CMB, as what cosmologists call parity asymmetry.
Yes, the resulting power spectrum, which we now call direct sum inflation, or DSI, predicts a very precise oscillating pattern in the CMB temperature data.
To understand this signature, we need to first remember how the CMB is analyzed. We break down the temperature variations across the sky into harmonic modes called multipoles. They're designated by the variable dollars.
Low values correspond to the largest angular scales in the sky, the vast structures of the universe. High L values correspond to small, localized spots.
And the standard theory, standard inflation, or SI, it predicts that the power spectrum, which tells us the strength of these fluctuations, should be largely featureless and scale invariant.
Meaning it should look roughly the same at all scales, including for even and odd values. There should be no preference.
But the DSI model predicts something very different.
It does. It predicts that the angular power spectrum, XDSI, will exhibit a specific oscillation between the even multipoles and the odd multipoles. It follows the relationship. C stellene left 1 plus 1 multipoles left as keypoles. That's a mathematical statement, but it translates into a very clear physical prediction. Power is suppressed in the even multipoles, the largest, most symmetrical structures, and it's simultaneously enhanced in the odd multipoles, the slightly asymmetric structures, relative to what the vanilla standard inflation model would predict.
And this is a critical distinction, because for over 20 years, cosmologists have focused on the low-power anomaly, specifically the quadrupole, 2C11-2s, which is an even multipole.
The quadrupole represents the lowest possible harmonic structure in the sky, and it has consistently shown significantly less power than predicted by our standard models.
Most of the scientific community just interpreted that low C2 stellars as a statistical fluke. Or maybe some exotic effect that happened right at the Big Bang, or simply cosmic variance, the idea that we only have one universe to look at, and maybe ours is just statistically weird.
DSI reframes the entire issue. It doesn't just explain the low power in C2 to T2. It explains the suppression of all the even multipoles and the compensating enhancement in the odd multipoles as an intrinsic feature of the DQFT quantum vacuum structure.
The two effects are linked.
They are linked by the same mathcal asymmetry. One causes the other.
And this is where the above-the-norm news investigation brings the decisive evidence to light. This parity oscillation pattern, this structural asymmetry, is already clearly observed in the latest Planck satellite CMB data, specifically at low tyflation.
The data isn't just statistically suppressed, it's oscillating exactly as predicted by direct sum inflation.
The anomaly is quantified using a ratio of power in the even versus odd multipoles. It's known as RET-TT.
The observed value of RET-TT from the Planck data is approximately 0.79.
And an RDT of $1 would mean equal power, which is the standard prediction.
So an RTT of anti-79 cents means there is approximately 20% more power in the odd multipoles than the even ones at these vast cosmological scales.
This asymmetry confirms the presence of the hidden temporal sector's influence on the quantum fields that became our universe.
And this asymmetry is also measurable in something called the correlation function, the DANA. Specifically, we look at DEMIC, which is the correlation between antipodal points separated by 180 degrees.
What does standard physics predict for that?
Standard physics predicts it should be close to zero. There should be no correlation. But the Planck data shows DEPIC is negative. It's an anti-correlation.
Meaning that if one part of the sky is hot, the opposite side is slightly more likely to be cold.
It's the visual manifestation of that Mathka mirror effect predicted by DQFT.
Okay, let's talk about the objective strength of this finding, because this is where the paper moves from interesting theory to empirical validation. The researchers used rigorous Bayesian analysis, comparing the posterior probabilities of the DSI model against the standard inflation model.
And this statistical comparison is absolutely crucial. Standard models, they often have free parameters you can tune, so they can sometimes fit specific data points, but they struggle to explain multiple related anomalies simultaneously.
With Bayesian analysis, you're asking a different question.
You're asking, which physical model is statistically more likely to be the true underlying description of reality, given the totality of the observed data?
And the conclusion is, it's just astounding. We need to be very clear about the magnitude of this statistical victory for DQFT.
When comparing the DSI model, which incorporates the DQFT structure of quantum bridges and that necessary mathematical asymmetry, against the standard scale invariant power spectrum, the results are definitive. Based on the combined probability derived from key indicators, including the quadrupole power TTL-Tyre, the asymmetry ratio Bohr TTL-Tyre, and that antipodal anti-correlation TTL-Tyre, the DSI model is statistically 650 times stronger than the standard model.
650 times stronger.
650.
That is not a marginal preference. In scientific terms, that is a definitive breakthrough. It's a groundbreaking observational confirmation of a fundamental, previously hidden quantum structure, the Einstein-Rosen temporal bridge, operating at the largest conceivable cosmological scales.
And this observed asymmetry, it's not caused by the universe being physically anisotropic or lopsided in a classic sense.
No.
Instead, it is an intrinsic mathematical symmetry that is embedded in the quantum fields themselves, directly reflecting the concealed temporal sector predicted by DQFT.
The arrow of time that defined the early universe was not singular. It was a dual-sector system.
This research effectively turns what was a historical anomaly of the CMB into the smoking gun, proving the existence of the dual temporal reality that was proposed by Einstein and Rosen nearly a century ago.
And this is exactly why we commit to bringing these in-depth investigations, like this one published in Classical and Quantum Gravity, to our dedicated above-the-norm news subscribers. What we have revealed today is truly the profound nature of the Einstein-Rosen bridge. We have moved it from a fantastical, non-traversable geometric wormhole relegated to the realm of science fiction to a mathematically proven quantum structure, one that is essential for maintaining unitarity in a universe that contains gravitational horizons.
The central tension between general relativity and quantum mechanics, the one identified nearly a century ago, it really lay in their incompatible definitions of time. Specifically, the failure of QFT to cope with the exponential instability of gravitational horizons, the physics of the inverted harmonic oscillator.
And DQFT, with the quantum ER bridge, it resolves this by acknowledging the geometrical necessity of dual orthogonal time sectors. This framework provides the first clear, observationally backed pathway to a unitary quantum field theory in curved spacetime without resorting to unproven speculative Planck-scale physics or these incredibly complex entanglement schemes.
The ER bridge is the temporal link that keeps information pure, even across the seemingly impenetrable barrier of a black hole horizon.
And the significance of this investigation stretches far beyond solving the black hole information paradox.
It does. This framework connects the smallest quantum dynamics, rooted in that IHO instability, to the largest scales in the cosmos, visible in the CMB. If these mathematical bridges exist, we are forced to fundamentally reconsider the nature of cosmic origins.
The idea of a dual temporal reality suggests that the entire universe may have emerged from a deeper time-symmetric quantum phase,
with the dual time sectors providing the underlying mechanism for all subsequent cosmic evolution.
It aligns conceptually with proposals like the bouncing universe or the time-symmetric initial conditions proposed by Hurdle.
Exactly, where the universe originates in a state where time has not yet chosen its single dominant arrow. And the 650 times statistical evidence from the CMB suggests that the arrow of time we observe is merely one half of a complete quantum reality.
And that the DQFT structure is still subtly influencing the cosmos at its largest scales.
That is the ultimate implication of this investigation.
We thank you for joining this deep insider briefing, and we encourage you to follow Above the Norm News for continued access to investigations of this magnitude.